All right. Okay, so here we go left off with number 5, and I kind of want to review number 5, okay, because this is what today and the rest of the year is about, looking at something called equilibrium versus our Q position, all tied to non-standard delta G, okay? So, looking at number 5, and I know we did this yesterday, I kind of want to review, okay? A small K view is problematic. So, let's draw a U diagram, okay? And I hope you have done that, all right? But, so here's my diagram, okay?
You are so funny.
I know, I'm so tall. So if my KQ is small, and let's not forget, okay, Q is equal to KEQ, or K, they're synonymous, and equilibrium is a position allowable by nature that shows, hey, who's a little more spontaneous? So if we got a small KQ, we know we're at equilibrium. We know equilibrium means that we're in that position, okay, that's showing us when the reaction dies, the universe is showing us the forward and reverse, who's more favored. So when I draw this diagram, okay, and let's go here, and if KQ is what, favorable, let's start more this way. Oh, I know people are hating that, okay, but hey, we'll start here, and we'll favor here, and then we'll go over here. So what we have is we have 100% reactance at this position, and then we have 100% products. And if, as you can see, in this position here, okay, there is going to be, this will be 50%. So KQ, or K will write, favors more reactance. And I'll put reactance for R and P for products. Because I already had that. Okay, now, and of course the reaction is moving from reactants to products. Now, with a small KQ, that means what? Well, specifically, it means that if you look at the position here versus this position, we have the dual, the competing pathways. Remember, if there is reversibility, that means that the delta G is not extremely negative or not extremely large positive, which means it's small. It can swing both ways, okay? Now, it's showing us when the reaction dies, clearly there is a much larger what? Pathway, thermodynamically, to go in the reverse than it goes in the forward. You guys saw an example of that, and that's insoluble salts last night. And if you're not following along with me, you can't do this. I can't help you. I'm giving you the keys to the Cadillac and earning your best possible score if you do the things that I'm asking. I'm asking a lot because this course is a lot now. So when I look at an equilibrium position, when the reaction dies, there's a favored amount. In this case, the reactants are favored. Why? Because the better thermodynamic pathway at the conditions that we measure is better a little bit than the reverse. So it makes sense that at equilibrium, there's going to be more what? Reactants than products. And since K equals Q, and what do they equal? The products over the reactants, concentration or partial pressures to their respective coefficients. And solids and liquids do not apply, just like last night. The solid did not apply in the equilibrium for KSP. Okay? So, when we measure this, the K in this case is going to be what? Small. Less than 0. So K is less than 0. Okay? And that means, and someone talked about it last night, that it's really hard. The smaller K is, the more it favors the reactants, the more it shows you that the reverse reaction is more spontaneous. That's impertinent, okay, as we look at this. All right? So very simply, the reverse is more spontaneous, which means that delta G, which is always written for the forward, is a little bit positive here, isn't it? And as KEQ, or that position moves and favors more and more reactants, the delta G becomes more and more positive. That should be intuitive. Remember, delta G is written for the forward. As the K favors more what? Products, then the forward reaction becomes more spontaneous and closer to negative. And how do I know that? Because we have this beautiful formula. Delta G non-standard is equal to what? Delta G, that's our fixed point, standard, plus RT ln of Q. But at equilibrium, this becomes ln of K. It's the same thing. But what happens is when this goes to what? 0, delta G of standard conditions is still what it is, plus RT. We solve for delta 0, so all of this goes negative. So delta G becomes negative RT ln of K. Hey, when K is small, less than 1, the natural log or log of it becomes a negative expression. This becomes now what? Plus plus positive. It makes sense. When the natural log of K is large, when there's more products than reactants, this is going to be here, showing us this forward reaction is more spontaneous. That red or pink, whatever color, fuchsia, is showing us who's more spontaneous. We're never going to get 50-50. So back to reality. Small Keq is problematic because the reaction does what? It goes forward only a little bit. Okay, in fact, the smaller the K, the harder it is to actually have a Q, an actual, remember K is that position when the reaction dies, and we always move toward it. It's hard to have a Q what? Less than K. It's hard to have a scenario where we have a lot more reactants and products if this gets smaller. Okay, so clearly products are favored? No. The reactants are favored over products as the reaction approaches equilibrium. Okay, so that's that problem. Now, as we move forward, okay, to number 6, true or false, reaction Q is just a current state of reaction, okay? Correct. Q, which is a reaction quotient, tells us exactly at that point, that snapshot in time, what the products and concentrations are as the reaction is running. That's why they call it a reaction quotient, okay? And Q is what? The value of Q when it reaches the death or equilibrium. Of course, that's true. You guys nailed that pretty well. When Q is less than K, remember, it's always a position of where the reactants are, okay, versus this position. So when Q is less than K, in this case, Q is less than K, and why would that be an issue? Well, why would that happen? What's Q or K? Products over reactants. Coefficients become exponents. Solids and liquids do not apply. I keep saying that because someone's going to get that wrong. Okay? So when Q is less than K, in this example, the denominator is bigger. Okay? And guess where we move? We always move forward until we reach the end. Okay? So, when Q is less than K, a forward reaction is spontaneous. Correct. We put ourselves in front in this position. I don't care where K is, but if my Q is less than this value, I know I'm spontaneous. Last night, KSPs, salts that are insoluble, actually do dissolve only when you have what? Values of Q that are less than K, but it's really, really hard to get there if this K is really, really small. But it is possible. There is some solubility. As I said last night, things that we quote say insoluble actually do dissolve. They just take tremendous amount of water to do so. The bricks outside this building actually dissolve. If there's a K, that means there's a position forward a little bit, which means the reaction has some ability to go forward before it what? Dies. Okay? So the forward reaction is spontaneous and the reverse is non-spontaneous. Best question there. Okay? There's a favorable. Now, moving forward, number 9, true or false? If Keq is very small, the reverse, I think I just did this one. Yeah, the reverse reaction. So Keq is very small, the reverse has a better pathway. That's what it's showing you. True. Only 60% got that right. 100%, hey, you should go over it. Le Chatelier's principle, shifting of a reaction is really changing the value Q with relation to Keq. Yes, every reaction has its position. And what are we doing in Le Chatelier's principle? I always tell you, hey, when you have very simple Le Chatelier's principles, we have something that is reversible, not something that's a completion reaction. What's the difference? When I burned a piece of paper, was that reversible? No, that's called a completion reaction. Combustion reactions are completion reactions. Precipitation reactions are completion reactions. Because Anytime this K is in an extreme left position, really, really small, or really, 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 really big, we haven't talked about this, we haven't been there. Remember this, party people? Kas of acids. What's an acid? Strong acid means what? It completely dissociates. This does what? Completely dissociates, correct? So what do you think the equilibrium constant of this acid if it's strong? Way over here. So high we say it approaches infinity because there's what? So many products compared to reactants. So we consider strong acids and strong bases as completion reactions. So any reaction where the what? The K is either an extreme small or big are completions. Okay, that's important. All right? And we'll get back to that. We didn't, I told you what it was, but now it means so much more. Okay? Myrrh, I think, is something that the three wise men brought. Okay, I don't care. Okay, so any case. Remember Myrrh, Frank?
Yes.
Yeah, sorry, I just went to religion school. All right, so number 11.
Okay.
If the right tank represents, now, my bad here. I feel bad, man, I'm over it. I sent you guys out the key because why? Okay, did I answer this question? Yeah, we did. So number 11 and 12, I resent out new keys because I made a mistake. I should have realized the low 8% is I did bad teaching, or, it's also a possibility, okay, in spite of me, or my key was bad, and it was. So let's go over this. Now, let's talk about if the right tank represent Mr. Grodsky. So we're going to redo this experiment. Okay, we did, hopefully you watched it, but we had this right tank, was me, and this was the student, I forget her name now. Okay, and they were the same size. And we had some, hopefully this is blue, but this might be purple because I started out with what?
Yeah, it's purple.
Okay, well we got purple.
Pretty much.
Okay, now I always know how I start because I get the bigger cup. So this is Mr. Grodsky. You can tell why. And this is...
Look at all that hair. Is that your evil twin mom?
No, it's me. Why would you not know? Okay, so the hair gives it away because it's a fantasy of mine. Why wouldn't it be? Now, the point is, okay, why is that funny?
She get away.
Why is that really funny? You're losing points as you keep laughing. At this point, okay, you can't pass this course. Okay. Okay, now, in the tank demonstration, this is the video I posted of me doing it, I had the bigger cup. She had the smaller cup. So I was gonna win. I represent, I know it's going backwards here, these were the reactants going to products. So this, I know I'm writing it backwards, I hope you can handle it. So the reaction's going this way. Now, what did you watch? Because I could scoop up more water than she could, this was the reactants were what? Going down, right? I guess I can just do that. And this was going what? You were seeing something change. There was a thermodynamic pathway. The reactants were becoming products, and there was a change in the value. That's not equilibrium. Equilibrium, and some people thought equilibrium is when these values equal the same. No! Equilibrium, I can't speak, is never this position, 50%, 50%. I wrote that initially to teach you, but it's always one way or the other because guess what? Can we ever really have a pathway that's equal for both directions? Think about thermodynamics. Absolutely not. You can't have thermodynamics giving me an equal what? Thermodynamic pathway for two directions because there's only one direction possible. It's the Bummer law. Now, one might be slightly better and you might approach it, but you never have 50% reactants and 50% because there must be always a favorable direction, which is what? Entropy of the universe increasing. Okay, it all comes together. Now, equilibrium occurred when eventually my tank, Christmas changing, didn't go black, okay, went purple, I guess, and her tank went what? Well, we were in equilibrium when no more changes were occurring. The concentrations were constant. The reaction was dead. There was no more free energy left, okay? Remember, this is a model. It's not perfect. So we were pouring forever, and this wouldn't change. Why? I couldn't scoop up as much. So I was only getting what? She was able to scoop a full cup. And what did I show you? What I scooped up actually filled up her cup pretty close. I was putting in the same water amount as she was. And that's what equilibrium is. The rate of the forward equals the rate of the reverse, and there's no change. It doesn't mean stuff isn't going, just means there's no overall direction. Okay, perfect. Now what did we learn from this? We learned that there was a pathway going forward. We also learned that at equilibrium, who was favored? When we reached equilibrium, who was favored? The products. So what do you think the equilibrium constant is? Okay, in terms of this reaction or the demo that I gave you. Where would it look now? Right. So if I like to let's put this in I don't know, purple, wouldn't it look something like this? Right, and now my what? My K is now here. And which arrow now is bigger? The forward pathway is better than the reverse. Now there's some pathway if we go, there's some pathway here, so let's change this up. So now the reverse pathway, I was lisping there, is what? Not as good as the forward for those that, so we just changed what? The K position. This process was clearly favoring the products. Okay? You good? So, the forward reaction is spontaneous. Absolutely. You saw me clearly do that. And by the way, yes?
Could the spontaneity change depending on the position of Q on the graph?
Absolutely. That's what Le Chatelier's is. When we change concentrations, remember I said I played Buddha, God, no, nothing yesterday? Okay? For instance, if you go here, to make this, if the reaction was here, which way am I going? I'd be always moving toward equilibrium. So that means that right now, if I put the Q in this position, which means what? Too many products that are allowable by the what? The competing pathways that universe allows. If I have too big of what? Of products, the reaction's going to move to lower the products. So if I want this reaction to continue to go this way, I would try to keep my Q less than K. And one of the ways I said yesterday is keep removing the products. Think with me for a second. Okay? If I keep removing the products as I take them away, my reactant value stays, well, my product value on top stays lower, and my Q will stay lower than K, and I can keep going until I run out. It's one of the ways that we play games in reactants. We keep taking the product. Cells do that. How do we keep having things flow into the cell? We keep using up the things that are diffusing, and by doing that, we keep the Q less than K. Okay? Sorry for saying K. Potassium. All right, so forward is spontaneous. Yes, there's a better pathway. Now, hold on, party people. Does this make sense? Hey, why would it be pathway? If K is big, it's greater than 1, sorry, right? Because products are bigger than reactants over here, yes? Then that's going to give me a positive log number, right? Positive times negative, this whole expression is what? Negative and a negative delta G, and G is written for what? The forward. It makes sense. All right? Hey, the forward reaction is negative delta G. Yes! Okay, Q is smaller than 1 if the right tank represents the reactants. If the right tank, I guess how we started, right? It has to be where we started. So when we started, I went forward. When I started the reaction, isn't Q had less reactants than it's supposed to? So didn't this reaction go forward as I went from small to big? So wasn't my position like right here? So Q, when I started, I guess I should have said that better, okay, is smaller than 1 when I started, okay? Because it's not Q anymore once it reaches equilibrium, it's K. So when the reaction was moving this way, okay, I started with low reactants. I'm sorry, bad Brodsky. I started with what? High reactants. So when I started with high reactants, I started with a smaller Q, and that's why this reaction did what? Move till I lowered my reactants, okay? Q is smaller than KQ, okay? Absolutely, you saw it go forward until the products increased. I know I'm writing this backwards, okay? Okay, so that's all checks. Sorry for those that got it right initially. I remember I reran them and changed the grade. Okay, this also was wrong. When equilibrium is reached, the rate of filling water from one tank to the other is the same. Correct. Q equals KQ. Check, check. Delta G is 0. Check. The K EQ value is larger than 1. Check. It favored the products. How did I know? There was a lot more water in her tank. She was the products. Okay, so they're all checked, so both of them. If you got them, good for you. If you learned from that, good from you. All right. And not sure why that's funny, but hey, I must have something on my nose. Okay, all right. Let's move on, party people. Okay, so let's go on to your extra credit test. I know you don't have it in front of you, but I want to talk about it. Because guess what? There's everything to do with this. So look at this reaction, party people. Now, from question 1 of the test, delta G was positive, which means this reaction did not go spontaneously. But look at the value, it's small. So there is reversibility, isn't there? Cool, cool. Now, what did I tell you? The concentrations, hey, brackets, molarity of the reactants and products are not at 1. If they're at 1, we would be at standard conditions. So we're at non-standard conditions. So the question is, what's happening when I make those values as a chemist? If I start the concentration, what did I do here? Well, what I said is, now you could speak to this, but anytime they say prove it, okay, I'm just going to use this. Hey, non-standard. I found my Q, products of reactants. What are these ones? Coefficients become exponents. These were all what? Okay, gases, so they're all good. And these are concentrations, and I found my Q to be 0.125. Okay, I solved for this. Now notice something, party people. Your R is 0.831. We've got to be what? In kilojoules, so I converted my R. People forget that. Are you getting it? Sorry. Now when I found 0.125, hey, that's less than 1. So that's going to be a what value? Hey, negative. This whole expression now is negative. And then when I add a positive to a negative, my positive value is getting smaller. Aren't I working towards 0 and a negative delta G? So by having these concentrations, aren't I becoming more spontaneous in the forward? Yes. So that's how you said it. Remember, this measures the what? Spontaneity of the forward. But I asked you about the reverse. If this arrow is getting bigger in the forward, what does that mean? It means that it's getting smaller in the reverse, so the reverse spontaneity is decreasing. Now you say, that's all I need to say? Pretty much. But let's look at Le Chatelier's principle. Le Chatelier's principle states what? Okay, whatever reaction that could be at equilibrium, if we apply a stress, we do the opposite. Hello? We start with 1, 1, and 1 under standard conditions, correct? Now, what did I just do? This guy is what? A reactant. I made the reactant bigger. Okay. Again, if the reactant is now what? 0.2, and I made the products what? Smaller. Ooh, I made this product smaller. This is a bigger number. What's the value? Right, now I could do this anyway, but Le Chatelier's principle, teaching Regents chemistry, stress, response. What did I do? I made those concentrations so that there's what? Okay, if there's more products, okay, what's going to happen? Okay, so I mean, in this case, we had more what? We had more. Yes, we had more reactants. Okay, so we increased the reactants. Sorry, all right. Sometimes I get lost. And therefore, the stress is there's too many reactants allowable by the position of K, correct? Wherever it might be. And therefore, the response by the reaction, really it's the response by the universe, which is allowable, right? Is that we're going to do what? Decrease the R. Now this, what does it really mean? If my R is too big, that means my Q is smaller than what? Right. Okay, so essentially we're going to shift to do what? Lower the reactants. And if you shift to lower the reactions, we're going to get a shift to, this is the what? You learned last year, Cashman, hey, your money on this, right? If I have too many reactants, the reaction is going to shift to what? Lower the reactants to make more products. How do we relate this to real chemistry? Hey, if you have too many reactants, your Q is what? Less than K, and you're going to work toward the K. Careful though, the position of K might make it harder to be in that position, but nevertheless, if you increase this enough, you will be less than K, and you'll move toward the forward direction, and you'll have a what? Okay? An arrow going forward, be more spontaneous. Many ways to say that. Okay? I'm fighting that you understand that. Okay. Now, let's go to Le Chatelier's worksheet that we had last night. Okay? This is the easy one, and I give this to you because you still have to have these skills. So if we go to the worksheet, let's go here.
Are we only supposed to do the front?
Yes.
Okay, I did the back.
Okay.
I know.
Now, party people, we did this earlier in the year because guess what? Weren't we forcing a battery to become more spontaneous than it naturally was under standard conditions? When we making a battery, lab number 2, we were trying to find the factors that we can increase the voltage. What were we doing? Were we really doing in lab number 2? Weren't we trying to create a condition with what? Concentrations of our ions that would do what? Shift the equilibrium, shift the Q in a position that was smaller than K. We were trying to move the Q this way so that we would move spontaneously. And anytime a battery approaches equilibrium, it goes to 0 volts. So that's what we were doing. We're trying to make the forward reaction more spontaneous. I gave you some basics, but this is the details. Okay, now, in multiple choice questions on our test, you will get these very simple questions where they say, hey, I increase N2, okay? If I increase N2, that's a what? Product. Ooh, so what do I do here? If I increase N2, the reaction's gonna do the opposite to decrease N2. How does it do that? The universe is going to move the reaction in a spontaneous way to do what? Get rid of the extra and shift it to the left. That's how we answered it in a very low level understanding. And sometimes you can just use that explanation. Hey, if you have too much of one, hey, it's going to shift to lower it. If you have too much of the products, hey, where are you? Q is greater than K. If you have too much of the reactants, Q is what? Less than K, and you move this way. That's what this is, okay? So that's all that is. Now, there's one little thing here that bothers some people. It's pressure. When you're dealing with pressure, okay, what I would teach my other classes that don't look at the real Le Chatelier's principle, what we say is, and you can get away with this in very simple multiple choice questions that can pop up, so you don't have to work with this math all the time, but the understanding is important. If I have an increase in pressure, what's the effect on N2? Okay, when we do a very simple, when we increase the pressure, okay, what we do is we count moles of gas. This has 2 moles of gas. This has what? 4 moles of gases. So when I increase the pressure, we count moles of gas. That's got 2, that's got 4, correct? So if I increase the pressure, aren't I putting them close together? Aren't I really increasing the partial pressures? And where is there more molecules of a gas? So aren't these partial pressures increasing more than the partial pressures here because there are 4 moles of particles here? So the reaction to lower the pressure is to make less moles of a gas. And that works. If I decrease the pressure, expand, that means we're lowering the partial pressures too much. And the reaction is going to shift to make what? More. Don't forget that. But what's really happening there? Aren't partial pressures here, except this becomes what? Parentheses? Okay? Now, I'm going to tell you something, and you have to be, please focus here. This works fine, but this is bad chemistry. Okay, we have it in our lower level chemistry class. You need to recognize this. When I say increase the pressure of what? That is too vague. That written that way on an AP test, you'd have to question that. Because how can I increase, can I add another gas? Or not? Let me think about this for a second. And this brings up the fizz keeper. Okay? Let's talk about this. I won't use my hand. Okay, let's talk about this. Here's the process. I have CO2 in my Sprite, and I have CO2 aqueous in equilibrium with CO2 gas. Okay, so it's going back and forth. Now, in a sealed container, the CO2 in my Sprite, actually, I should probably, because I have to pay them things if they're my video, but in any case, the CO2 in my Sprit, okay, that's missing the E. Okay, all right, now, the CO2 in this drink, okay, carbonation is leaving until the pressure builds up and the rate of what? Of CO2 leaving is equal to the rate of the CO2 going back into solution. Aqueous, back to gas. You with me? Because it wouldn't keep going because this would explode. It reaches equilibrium. Now, they sell these things called fizz keepers. Okay, and all they are one-way valve pumps that push air into the top. So you just open this up, CO2 just left, and they call it the fizz keeper. Now the fizz, of course, is the gas. And what they suggest is, if you pump this up, now it's harder for me to, as I pump this up, the pressure is going to what? And if I increase the pressure, based on the simple idea, won't I, how many moles of gas on this side? How many, I have a gas, don't I? So I have 1. How many moles of gas here? 0. According to this, if I increase the pressure and I add gas molecules in a one-way valve, okay, I would force the reaction to make less gas, correct? The reaction shifts that way. But it does not work that way. What does these shifts really mean? Always. It means that. It means the Q. Party people, if I put more what? What's going into this bottle? If I put in nitrogen, 80% of the air, what? Nitrogen, 20% is oxygen. So I'm putting nitrogen and oxygen. Think with me for a second. So I'm pumping this up with another gas. Is that gas in my Q formula? Is it part of the reaction? So is it changing Q? Absolutely not. Theoretically. I want to make sure you understand this best. If you do not have something that's in the Q or K formula, changing it has no effect. Sometimes it can have the opposite effect, okay? And we saw that if we have something called a common ion effect. We'll talk more about that. Let me talk about this again, because I don't think I explained it as well as I'd like to. So we have a soda bottle of Sprit. Okay, that's an ugly bottle. All right, now, we know that the gas CO2 is in equilibrium with the aqueous going to gas and the gas kind of condensing or becoming back into solution. That's happening. Okay, now, if I was to pump air into this, let's say I pump in another atmosphere of air, okay, and I'm just going to write air here. Okay, so now in here, there is 2 ATMs. Now one of that ATM, let's pretend, is CO2. The other ATM is what? Air that I added, correct? For a total of 2. Now, when I open the bottle, and we know you hear the pressure, okay, equibulate with the pressure in the air. Now, this bottle, now of course the air and the what? CO2 mixed, didn't they? Here's my X, here's my air. So they all mixed correctly. Now there's 2 atmospheres. They're going to equibulate to what? To 1 atmosphere, correct? I had 2 atmospheres in the bottle. When I open it up, it's going to go to 1, correct?
Yes.
Because gases are a mixture, what's going to happen is to lower the pressure to 1, doesn't half the pressure have to be relieved? And what we know, half the molecules have to leave. Therefore, what did I just do to the CO2 gas molecules? I lowered the products so that now Q is greater than what? K, and now even more CO2 is going to leave. Do you see that? By adding more of the air, when I open up some of, under higher pressure, 1 atmosphere leaves. Therefore, some of the air and some of the what? CO2 leaves. And we just created a scenario where we've got less products than reactants, and so more CO2 comes out. This has the opposite effect. Okay? Cool beans if beans are chill. Is that boiling right there? Good. Okay.